Hey everyone, how are we doing? I have been working around with UT Verse, really fun stuff, fun, exciting things. We are streaming live on the YouTube now, but it is going to be time to jump in here to probably some Stat 201. But does anyone else have any questions? I can't wait to get contacts again. I got used to wearing glasses a little bit here, but you know what? Having contacts back would be amazing. I would love it. I ordered some. They should be coming in probably like a month. If I were to get them, I think I ordered them this weekend or last weekend. If I were to get them sooner than later, that'd be amazing. It would make my day. Let's go look at what Stat 201 has right here. Stat 201. A few people have turned in their projects. 8 people have turned in their projects so far. And what is coming up due right here? We got chapter 16 tomorrow, and we have Canvas content. Maybe we'll do Canvas content hypothesis test right now. That's an easy one to knock out. Just looking at the project, seeing how they're looking. Okay. Seeing the matching percentages. I'm looking at those right now. I laugh and I'm like, please don't have high matching percentages. Please. Only one in the 30s, and I'm looking at it now. Looking at how it goes. Okay. They only match, okay. Yeah, they're fine. Yeah, it's literally the things we would expect, where it's like, yeah. It's like things that everybody would have, like confidence interval, overlaps. The overlapping things are, if you saw them, you'd be like, okay, this is exactly what we would expect to see overlapping, like high blood pressures overlapping, like someone with high blood pressure, like, yeah, it's all, yeah, no cheating. But hey Katie, good to see you there. What questions do you have? We can do whatever. You're first here, so we get to do whatever you want. You name the thing, we do the thing. For some reason I'm like, I'm gonna go grab that Vita water over there. You know what, I'm gonna grab that Vita water and we'll start up. Drop your questions in the chat. We can do some Stat 201 or some 320. Good to see you there. Yeah, so I can't show the KUB data on stream because it's like proprietary data. So with that data right there, so I can talk about it a little bit here. I'll turn on the music. With the data, what it is they recorded an event. So every row of data is an event. Because I went through and rewatched everything last night and refigured it out and just refreshed all my memory, because I was like, I'm asking you guys to do it. So I was like, why don't I do it too? Why don't I sit down here for a good bit of time, probably about only an hour and a half that I sat down. Yeah, so the graphs, and I'll probably go over those during class a little bit too, because I posted a lot of graphics and information, which I'm not going to display here because it's kind of like we'd be putting on YouTube. So I can tell you the theory behind it right now. Is every row of data is an event. And the event is that there's either low voltage or a recorded brownout in that area. So we literally have right now events of low voltage or brownouts. And that's what everything is right there. So if we're seeing something, it means something tripped a sensor that recorded the data, which is kind of a bummer because it means we're looking at frequency of low voltage or brownout events. So it doesn't mean it's a brownout for certain. It doesn't mean that the voltage went so low that people are getting intermittent power, which is what a brownout is. It means that there's either a low voltage alarm gone off or a recorded brownout. So we're kind of looking for the commonality among these. We might need to do some cluster analysis, but I can display that in class today. But what I did, one of the graphics I made was I made a chart that looked at the frequency of brownout or low event voltages by week, and you see like this spike pattern, and I'm like, why is that? When is that? So I'd really like to know, might even make a chart of like, we might need to look at historic data, because there might be something with the historic data that would tell us what was going on in Knoxville. Probably want to look at the locations of where those occurred. And then morning, Noel. So there seems to be some, what I noticed last night from my looking through the data is that these events do have some time order pattern to them. It's definitely not linear. There is a slight linear uptick at the end of the series. If you look at the series, it goes like boop, 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 and then it goes whoop, a little higher, and then boop, and then the last series has 2 bumps at the top. If you're looking at the Discord series, so so when we're using GLM is used to predict logistic models. That's when we're predicting the probability of something occurring, like the probability of a brownout. So we might actually list some of the things as brownouts, or we could list low voltage alarm. Oh, we're talking about KUB data. So what we might do today is we might try to better put them into the grouping of brownout or low voltage alarm. So some of them are not that low voltage. I mean, they're low voltage, like it was tripped, but there seems to be this 213. I'm going to show a lot of what I figured out today. So what I would suggest doing is making a categorical variable of brownout or low voltage, but you can use LM on the data. So you don't have to use GLM, because this assignment is like all your knowledge. If you're predicting min voltage, why would you use LM? If you're predicting min voltage, why would you use LM? And Noel, this goes to the end of the project right here. Then we're going to work on some hypothesis testing campus content. Why would you use LM to predict min voltage versus GLM to predict brownout or low voltage alarm? So you have to think of the key difference between logistic and linear regression, which is a huge part of the class. Boom! Let's throw Caitlin. Just got Katie right there. Got everyone 5,000 points. You're 100% right. Because quantitative variables are like min voltage, like it's a quantitative amount. So we can make a linear model to predict that. We can also think about polynomial models, interactions. We can think about nonlinear, well, polynomial models are nonlinear chance. We can do segmented line models. There's so many things we can do, but we're going to start with the simplest things with probably a simple linear regression. That's why ChatGPT is great, but it's probably it can do like crazy big things to start, and then you don't do the small things, which you should always look at the small things. As a famous song once said, all the small things, do them first. I think that's how the song goes. So looking at a simple linear model, 1x, 1y to do is good. Chapter 16, yeah, the quiz. You drop some quiz questions in here, Noel. You got it. We'll do some quiz questions. So does that make sense, Katie? Is to first start by thinking, what is the y variable of interest? The min voltage seems to be a huge thing right there. I've been doing linear models in GLM to get some summaries of the data to see what stands out. Exactly. And it's tough. Yeah, and that's why, especially like you look at what we're doing in class, we're just kind of brainstorming and working with it. And that's why I was like, I need to go back and watch this video, because I was like, I'm going to come to class tomorrow with tons of stuff. I got tons of ideas today, especially with what I posted on Discord. I was like, ooh, look at this. Ooh, look at this. Ooh, look at this. And I realized I'm also walking into this with 14. I mean, I don't know. I've been doing SAS for 23 years, been teaching it for 14 years. So I come in with a much bigger base of knowledge. And the thing I did is called statistical process control, which is something you learn in Stat 340. So I had to pull out a knowledge from another class, control chart knowledge, to look at the frequency of low voltage brownout events by week, and to create a chart that showed if things are out of control. Now, what's interesting, and I'll point out in class, is something out of control is more than 3 standard deviations away, which is an unlikely thing, as Noel probably knows. 99.7% of data is within plus or minus 3 standard deviations, 68, 95, 99.7. A company survey, you got it, Noel. I double copy his numbers. I've noticed that. That's what my person does by default. So a lot of these topics you learn in 201, 320, they're used in every statistical discipline. The idea of, you know, how many standard deviations do we go out? And I think that's a good step right there, Katie, is to make some simple models. And you're not, Mary, you're not working this job. This is not like your job. This is a tough job, because we have to come in with learn things about brownouts. We have to understand the data, and then we have to know how to use the statistics on the data. And we're literally doing what someone would be doing as a job, like trying to get insights to, oh, no worries, you're fine. We're literally doing what people would do to get insight to make decisions about what KUB should be doing and looking out for. So it's like, how can we be proactive and how can we be reactive? I'd say more being proactive. So now we're looking at prescriptive analytics. If we can understand why brownouts occur, we can be more proactive and act before brownouts occur, or expect brownouts, or even predict, because then we can act where they're going to occur, predict where a brownout might be likely to occur. So yeah, and we could put warnings out. We could check units quicker. So it would help if we had more data. It would help if we had data collected at random intervals from all the units, that if we knew just at random points how like, or if we knew all the units, if we had a data frame of every single unit they had, and then we could connect that to how many brownouts events occur per units. So that'd be something. This is future research. We're talking about, if we talk about the STATS1 project, what I would want is a list of all their, I think they're transformers, all the units, and then we could link that to how many brownouts events have occurred per unit, and we could look at per location, and then we could see if there's a commonality of why brownout events are occurring based on that unit, where it's located, the age of the unit, the amount of precipitation that units got in that area. Like, we could figure out rainfall in that area over a certain amount of time. Maybe certain things are affecting it that, we would have to figure out. But I mean, this is a huge project. Someone could spend months working on this at a company. And we're just we built up months of knowledge to spend 2-3 weeks. If I show you what I have so far from AI and not from doing it, send it to me on Discord. I'll try to take a look between classes and everything, or I'll take a look between talks right here. But send it to me on Discord. I'll take a look. I'll give you my thoughts. And we'll be doing lots of sharing and kind of going over everything today. That's the point. Like it. Okay, with that, we are going to do a little STATS1. Good job, Katie, right there. It's a tough, this is literally a job we're doing. We're doing a job right now. We got a job. We got a job working on KUB data. And I emailed them and asked them if they want to swing back by. So we'll hopefully hear back on that. And we put it here on the stream. So BAS 320 final project discussion. Okay. You're welcome, Katie, and great job. Great job. Good work yesterday. Good practice. Just keep asking any question when something doesn't work, because literally, I can't tell you, this is the last thing I'll say on this. The first semester I taught 320, I had my computers beside me with the answers, and I would be working and I'd be like, okay, so now we're going to do LM predict. And I would be copying straight from the answers because I'd be too afraid to code it by like just trying to do it without the code, without looking at the answers. So when I was in class and we'd be going over stuff, I'd be like looking over the answers, like going between the answers and like writing. I'd be like, now we're going to do this. And a student would be like, why do we have to use GLM or LM? And I'd be like, let me, I'll get back to you on that. I'll send you a reply, and then I have to go Google it. And I mean, you kind of know it and you kind of don't. It's tough. Like, you learn these things a lot better over time, that the GLM is the generalized linear model, the LM is the linear model. And the reason we use LM instead of GLM for the linear model, because you could do it with the GLM with family equals Gaussian, is because Petry's codes are set up to do the visualizations based on if it's GLM or LM. So if we switch over to ggplots, it actually doesn't matter, as the rock says. We could use LM or GLM for linear logistic. But if you're doing logistic, you have to use GLM family binomial, which means a 2-level categorical variable Y. So you just teach something for like a decade, and then you can answer all the questions because you get asked all the questions. Yeah. I coded a little bit as a kid. I didn't code a lot as a kid, but I would do a little HTML coding and I didn't even know it. There was a game we had, we were like this fish, and I noticed these things like FF8200, and I was like, what's that? And I changed some of it and the fish changed colors, and I was like, that's weird. I was working with hexadecimal color codes right there, and I didn't even know what hexadecimal was. And then I started to change other things like speeds of the fish and other things, and like I didn't realize I was storing variables like the speed of how fast the fish went. So I was kind of like vicariously did a little bit of code and didn't even know it. I was randomly editing HTML code. And I think through those experiences, I then had the opportunity to code. And I was like, I remember this. And also I grew up doing DOS shell. So I don't know if I can show it on here. Command prompt. Oh man. Here we go. I'll show real quick. When I was a kid, I had to load my video games like this. I had to be like, oh man, make directory, Brian is awesome. Change directory, Brian is awesome. So imagine being a kid, and you have to remove Brian is awesome. Oh, remove directory. I don't know how to remove a directory. So imagine being a kid and you have to load your video games in. Have you ever done the color code thing with ChatGPT to find out what colors look best to wear? Oh, really? Send me that, Katie, right there. That sounds very cool. So when I was playing my Sierra games when I was a kid, I had to do these things right. I didn't do a lot. dir \p, dl start out star. Don't do that one. Don't do that. Or format c colon. Don't do that. Don't format your C draft. But I was, putting in a function with the command. Like if you think of this as we do in 320, the command make directory has one argument, or the function make directory has one argument, and the argument is what directory do you want to make. So I didn't even realize it, but I was kind of working off these ideas of functions. There's a lot of tangential knowledge I had. Yeah, and so I'm lucky because I grew up with, I had to learn how to, do, DOS shell or command prompt, and we had to like, and I had to like build things. I had to like make shortcuts to my games. I had to put in the command it had to run. I had to be like, okay, it's in this directory, run this command right here, run this file, run this exe executable file. And so it's something you just learn over time. So I grew up coding, kind of. A lot of knowledge I started out with, and then, yeah, shouts to your brother right there, Noah. That's awesome. We will do this quiz right here, and then we'll do your question, Noel. So we're going to put this in the video right here. Canvas content. Okay. Stat 201, Canvas content quiz number 9. Number 9, and this is hypothesis testing. Okay. So this one totally destroys people. This question right here, people that say, I've got no idea how to solve this. Well, what in the world is going on? This question is all about that
notation,
brother. So here we are. A new diet is being tested. The inventor claims people will lose 10 pounds on average after 6 weeks. 25 people are randomly picked to try the diet. Researchers are concerned about the investor's claim being exaggerated, which means they're thinking it's too high, that the actual value is lower. The sample yields an average of 3.14 pi, and a standard deviation of 7.2. Calculate the t statistic. It says appropriate test statistic, but we're doing a t. So Noel, do you know any of this notation right here? Do you know anything on this screen? Any of these values? Any of these things in notation? I'm being tricky. I highlighted one more than's needed. What I'm doing when I get to problems, I usually look at numbers first, and I'm like, well, the numbers are probably notation. So what is the notation right here? I have highlighted way more numbers that need to be highlighted, but you want to be able to identify the notation when doing questions, and then you can solve it. There should be a few easy ones. Are there any? Close. The inventor claims. So that is mu naught. That is the hypothesized truth. So that means the null is that the true mean is equal to 10 pounds. And since we think they exaggerate it, the alternative is the true mean is less than 10 pounds. Remember, the only thing that changes between these is the sign of the alternative based on the researcher's question. Researcher's question determines the sign of the alternative. So do we see anything else here? And good shot. Let's give you some points. Do you see anything else in this? Anything else? Don't worry. Any other notation? I'll erase one that doesn't matter.
It doesn't matter.
Boop. You're right. I think n is 25. You're right. I'll erase another that doesn't matter. Anything else? For each one you say that you get that matters, I erase one that doesn't matter. Here, wait, check this out. It says the sample yields an average of this. And specifically, we would call this S right here. And it says the sample yields an average of this. So what would that be? So the sample yields an average of this, and the sample yields a standard deviation of this. Remember, it's sample. You're really close. You basically have it. Not p-hat. Good guess. 5,000 points. Good guess. Sample average is y bar. P-hat is used for the sample proportion. So that is correct. It's sample, but that would be sample proportion is p-hat. And so now, if you notice the notation we have, we're actually doing y bar minus mu naught over s over square root of n to solve for the t statistic. which is the test statistic we've been trying to solve for. So it says solve for the appropriate test statistic, and that is the t right there. So now, go right there. Good job. So now we need to go and put in the numbers. We have right here the sample mean of 3.4 minus 10 over, and then S, which is 7.2 over square root of 25, which is 5, equals, oh, brain, come on, think harder. So it should be 0.6. Is this going to be 1.19? No. 1.44? 1.44. Good, I got it. So divided by 1.44, because that's 7.2 over 5. And then this is negative 6.6. So we should get something about negative 4.4. Negative 4.4. Negative 4 point that. There we go. Nice job, Noel. 5,000 points. Thank you for checking my work. Negative 4.58. You are correct. That's it. That's the test statistic, which would actually lead to a p-value of basically 0 because we're so far off the curve. So the end of this test would be as follows. If you're doing the full version of the test, you'd have to go to the t-applet, enter a t with 24 degrees of freedom, which is n minus 1. You'd be down here at negative 4.58. And the area below it is basically, the p-value is basically 0. And we can see this visually. This is where if you've done the t-applet a lot, you should be able to understand what you do with the t, the sign of the alternative. Maybe I should have done that in blue. The sign determines, yeah, it's more than 3 standard or 3 standard errors technically away, which means it's way off the curve, right? So great job, Noel, with that, because if it's more than 3 standard errors away, it's way off the curve. So 24 degrees of freedom, find the p-value using t. And now we enter in the negative 4.58 and we go below, and the p-value is basically 0. You can't even really see it. It's so small, it's off the curve. So does that make sense, Noel? You're totally right. The p-value, which it didn't ask for, is off the curve, or it's like so little that we can't see it. But yeah, it's more than 3 standard deviations away, which means a p-value that's very, very tiny. So we'd reject the null and think that the true weight loss is way less than they are claiming it to be. So good job. That is a great question. Know how to solve and go further and find the p-value. Next one's pretty easy. A new diet is being tested. The inventor claims people lose 10 pounds. They believe it's exaggerated. So the null has the what? The null has the what? This question is a lot easier if you know that the null always has the what. And we talked about that just a second ago. The null has the what? Equal sign. So now how many answers are you down to? If you know the null always has the equal sign, you only have to pick between 2 things, 2 answers. So if the claim is exaggerated, we'd be looking for evidence that people lose what to 10 pounds? People are saying, I want to lose weight. And they're like, you'll lose 10 pounds. I say, I think that's an exaggeration. I think you lose what to 10 pounds on this diet? We just did this one. I think you lose what to 10 pounds? I think you're exaggerating the weight loss. I think the true weight loss is what? Less than, and there you go right there. That is what we're looking for, evidence that you lose less than 10 pounds. And you can see we wrote it out in, I'm glad we got those back to back. So we wrote it out right there for this one, which was the same idea. Researchers' question is what tells us the sign of the alternative. Sign of the alternative. Low p-values are cause and effect. We have some bad words in this class. MuBot even knows it. So, we're going to even update MuBot, Noel, right here. We're going to have a little fun. So commands. Let me go to commands. So watch this. Where's hello? Let me get hello. Right, here we go. It's $sign username. Okay. Command. Let's say cause. Okay. Okay, I want you to say cause now. I want you to say I want you to say cause in the chat, Noel, and see what happens. Say the word cause. Hopefully I don't have 2 commands on it. Let's see. So MuBot should reply now with that. There we go. I wanted him to say people's names with that. MuBot now knows we don't say cause in this class. I know, right? I like it. I had to go over here and I'll show you. He's got a whole command section, and so I had to, it's a little, that's code right there. that has it look at your username. It can do, I think it can do time or something too. I'll have to look at what else it can do. And I can unenable it. And then he's just got lots of commands. Like we have so many commands that I've written. Like everything I do, like when I do, you know, there's TI, I forget I have TI tutorials. Will, you will lose points unless your name's Will. Elisa rocks from our SI leader. So Mubot has tons of cool things in there, and we don't say cause. So the answer to this is definitely what? Low p-values are evidence of cause and effect relationships. We don't say cause here. So the answer is definitely what. I'm trying to tell you what with this by saying it's a bad word. It's false. They're evidence of an association. We don't know if it's cause and effect. We have to do a designed experiment with that. We don't teach that in Tool 1, but we don't get into that. Here's what we covered yesterday on type 1, type 2 error. In a type 1, the null is what? In a type 1, I'll go to the main screen. In a type 1, the null is true and we reject it. In a type 2, the null is what and we what to what it. In a type 2, the null is and we to reject it. Someone added an extra 2 on us yesterday. I liked it. The null is false and we failed to reject it. So let's go look at the question. A type 2 error is when what? I mean, you just said it, Noel. The null is false and we failed to reject it. Look at the 2 F's of the type 2. It literally has 2 F's. There you go. In a type 2, the null is false and we fail to reject it. So 2 2's. When we reject the null and it's true, we've done what? What have we done, Noel? These are great. You're like, wait. When we reject the null and it's true, what kind of error have we made? Rejecting the true null if the null is type 1. That's easy. I try to make up memorization ways that we can get it done and get them right. So in a type 1, the null is true and we reject it. In a type 2, the null is false and we fail to reject it. No. And huge shout outs once again to Hannah. Came up with that. We think it's exaggerated. This is a difference of 1.1. That's 1.5. 1.1 divided by 1.5. Well, it's negative 1.1. It's like negative. I'm doing it in my head. Oh, wait, that's a 15th. What's a 15th? It's 0.66 plus 1/15. A 15th is less than a 10th. The 15th is like 0.07. So it should be like, think about that. I think, right? Should be close to it. Okay. Close to it. Yeah, that's about right. 2 decimals, we should be good. Small p-values provide strong evidence against the null. I got it right. Nice job, Noel. So this one, I love how we have no text provided. Great job. Strong p-values or low p-values would provide evidence for the alternative, which is evidence against the null. I'm going to say true. I don't love this question. I would prefer to say evidence for the alternative, but it's evidence against the null, evidence for the alternative. We don't have evidence for the null. We can have evidence to reject the null. I would prefer that. If small p-value provides strong evidence to reject the null, we have evidence to reject the null. We have evidence for the alternative. So I think, yeah, like evidence against the null to reject it. Yeah. A type 2 error is when null is false and we fail to reject it. And when we reject the null and it's true, we made a type 1. Might have got one wrong. No. Low p-values are evidence to reject the null. One more time for fun, then we're going to do your question, Noel. This is a difference of 4.1, negative 4.1. This is 6.6 divided by square root of 25. Once again, check out the earlier parts where I did this a lot slower. I'm just showing that if you know the formulas, you can kind of think through them, take good guesses. I'm doing this formula. If you're watching me do this, please check out the first question we did at the start of this section where we did this by every step. You should be able to label all the notation. So if you know all the notation, you just think through it and you say, okay, negative 4.1 from 10. And then we divide this by 5. We get 1.32, I believe. Negative 4.4 divided by 1.32 is about negative 3.2. 0.27. I'm gonna get that one wrong. We'll get close on that. We'll get close. We're looking for evidence it's less. Type 2 error is when the null is false and we failed to reject it. Small p-values provide strong evidence against the null. It's true. Evidence to reject it. If we construct a 95% confidence interval that does not contain the hypothesized value, which of the statements is true? We would reject. Ooh, thank you, Noel. My guess was not way off, but I trust Noel. Great job, Noel. 5,000 points. It's just solving that formula a bunch of times. So we've already done once. I just like doing it in my head. So if our interval does not contain the value, we would what that value. So 95% confidence intervals naturally relate, and I wish we had the slides up from yesterday. 95% confidence intervals naturally relate to doing a 0.05 alpha level. I trust you, Noel. So does that make sense? Inside, outside, and if it does not contain it, we can reject it. It's like saying I am 95% confident the true price of a steak in Knoxville is between $30 to $40. Well, then you could reject something like $42 because it's outside the interval, and you would reject it with the 0.05 alpha. Let me draw that out for people who weren't in class yesterday, as I know other people watch the video too. But if you have an interval, it looks like the following, and if you do a test, a two-tailed test, it looks like the following. Notice the interval shades the inside, so you'd have 95% inside. If you did, you would have 5% outside, and it'd be in the two tails. So this is relative to alpha equals 0.05 on the two-tailed does not equals test, where 95% confidence interval is relative to a two-tailed test with 0.05 alpha. So if the value were to be over here, then that means when you ran a test, you would have landed over here. I should do that in a different color. So theoretically, the value's over there, and that means you would have landed, we'll just go with a nice light purple. You land there, which means you land here, which means the p-value is less than alpha. The alpha is the shaded region, and the p-value is the darker region right there. So your p-value has to be less than alpha because where you landed is outside the interval. So if something is not contained in 95% confidence interval, you run a test, you would get a p-value less than 1 minus confidence interval level. So we can reject it because it's not contained in the interval. Your project goes over that also. I think got everything correct. And Noel, you are right. I said it before I even saw it because I believed in you. Great job, Noel. And let's do that question you had right there. On, where is it? A company surveyed. Let's do it. Company surveyed. Let's go check it out. My eye was bugging me and I'm glad it's not anymore. Well, hey, pretty much everyone but 16 people did the homework with an average of a 98. I like that. That's really good. Sad that, what is that? Very little percent of the class didn't do it. About 4 or 5% of the class didn't do the assignment at all. But we had a lot of people do it, and 98's pretty darn good. 98% average, I'll take it. I will take a 98% average on a homework. So let's go to the quiz and do the quiz question. We're almost done, Noel. Oof, there's a lot of questions here. You guys, you see this? What? I'm trying to move it here. Okay, let's go do it. Company surveyed. These are fun. They're good questions. They're good theory. Where is the company surveyed? Oh my gosh. Look how many questions I gotta go through. A lot of people get stuck on that one. Here we go. Oh my gosh. Look how many questions they list here for the conditions. So the first thing we're going to do is we're not going to read their conditions. We are going to look at, yay, good job. We're going to think about our conditions right here and which conditions we would have. So with this, they surveyed 2,000 men where 1,020 of them identified themselves as being the primary grocery shopper. So what are the three conditions? Don't even look at what they wrote. What are the three conditions? What are the three conditions? They surveyed 2,000 men where about 1,000 something of them said they're the primary grocery shopper. Don't even look at their conditions. This is where you practice for the test, where you don't look at their answers. You say, random, first condition, always randomness. So did they take a random sample? Sure, probably good to assume. And then what next? Random? This is a pretty good question on the way they have it. It lists a lot, but random. And then what's condition 2? I always focus on being prepared for the test. Like, I ignore what my Pearson says. I'm like, that is not wrong. So, Noel, you are right. That is a condition we will use. The second condition, random, 10%, and then success failure. So just to review again, it changes when you get to the third condition. That's where we pause, and pause is not a condition. But I always like to show this. People have probably seen this a million times, but take a screenshot of it, save it. And whenever we talk about conditions, go to the review 3 page. And on the review 3 page, you'll see down here a video that has all the concepts reviews, really good videos, probably some of the best videos to watch for the test. And if you go here to the end, you can see all the conditions with we are doing a proportion test, it looks like, because we're dealing with categorical data, which is yes, no data, categorical proportions, and random 10% success failure right there. So we won't be dealing with nearly normal. That is a trick by them to include nearly normal. So randomization is probably met because we probably took a random sample. Is satisfied, so there's nothing to indicate they were not random. 10% because 2,000 men is way less than 10% of all men. And then success failure is met because there's at least 10 successes, at least 10 failures. Yeah, no, you did great, Noel. Let me throw you some points. You are correct. There was nothing you said that was wrong. I just usually do random 10% pause to figure out which one it is. And then this was success failure. And you can see the amount of successes here for creating a confidence roll. How many failures were there? If there was 1,020 successes, how many failures were there? If there was 1,020 successes, how many failures were there? Well, 2,000 observations. You're right, Noel. And that's how many failures, because successes and failures have to add up to total sample size. So you can see that's how many successes, that's how many failures. And all success and failure means is group you're looking at, group you're not looking at. It doesn't mean positive or negative sentiment towards it. They now ask you to make a 98% confidence interval. So we're going to have to know that notation.
Notation, brother.
We're going to have to know it. Okay, let's do it. Here we are. You'll notice there's very little for this question, but we can still do it. Do you know any of these values on the screen right here? Do you know any of those? Because the formula for a 98% constant is p hat plus or minus z star, which is relative to 98%. Put 98% z star. That is 2.3263. I'll show you how to get that in a moment. Square root p hat q hat over n. So what is any of this notation? Can't remember which one Mubot responds to. I used to do exclamation in front of a bunch of things, now I don't as much. What is any of this notation? You're right, that is n. And then what else? The more you solve these, the better you get. And then I like to pause to see people figure it out. And don't worry if you get it wrong. Just practice. Just practice right now. We'll throw you some points for right answers. Throw points for wrong answers too. What is the other one? That is n. So we figured out n. While we're figuring out the next one right here, I'm going to show you, if you go to the applet, you want to go to between and find the x using p-value and type in 0.98. It is, you can do it to 2 decimals, 3 decimals. 3 is good, 4 is enough, but that's where I got the 2.3263 by shading the middle 95% of the curve. A lot of people get stuck on this one because it's not in the formula right now. But I think a lot of people know it theoretically. If I ask you 6 out of 10 people own bunnies, then you could probably say 60% own bunnies. So you're already doing the work. You just don't realize you know what it is. This is x. X over n equals p hat. So 1020 over 2000 equals, this is going to be 51%. That means p hat is 0.51 and q hat is 1 minus that, the complement, which is 0.49. Always remember that p hat and q hat are complements of each other. Well, remember, p hat has to be a number between 0 and 1 because p hat's a proportion. You can multiply it by 100 to turn it into a percent, but always express it as percent when you do. So p hat must be between 0 and 1. Q hat must be between 0 and 1, and it would be the complement of it. So double check if you mark something as p hat that it must be between 0 and 1, unless you're expressing it as a percent, but usually when doing the mathematics, do it as a decimal. Good job, Noel. Let's throw some points. Does that all make sense right there? P hat must be a number between 0 and 1. And all we're going to do is just plug in the numbers right here. There we go. And good work. Yeah, it's just practice. A lot of people forget what X is. That's why I always pause on X, because I've noticed it's just a common, like, because it's not in the formula. It's just one of those, it's like an intermediary step. So you have to like know to solve for P hat. And square root. That is the standard error, 0.01117. There we go. So that this, everything over here is the margin of error. It's the plus or minus on an interval. And we're going to times the standard error by 2.32. And there's the margin of error is 0.026, which is 2.6%. Great job, Noel. And then we just add and subtract that. So if you add and subtract it, you will get 53.6. Sure. And I'm moving it to percentages, apparently, what I did. And then you get 48.4. All we're doing is just adding and subtracting to get the lower and the upper interval. And it could be 0.484 or 0.536 as a decimal, or percent, 48.4 to 53.6. And so that's the interval. Let's go back to here. And it wants it as a decimal, so 0.484 to, really? 0.536. There we go. What does the confidence interval say? Because, interesting, because blank percent, they're asking, do we believe 46% is the truth? Is 46% in my interval? No, 46% is not in my interval. Since 46% is not in the interval, we can reject it. So we have evidence that more than 46% of men identify as the grocery shopper in their house. This is, once again, using the confidence interval. We just talked about this a moment ago to do the rejection of a value. So it's saying that P naught, or P, excuse me, is equal to 0.46. It's assuming that the truth is 46%, but our confidence interval does not contain it. So we have strong evidence that more than 46%, we can reject it. Determine the level of significance. That was done. And I think it says, now this is a tough question. Naturally, confidence intervals like a 98% confidence interval would have a what percent alpha? Here's a good question, and this is more like our test questions. Naturally, a 98% confidence interval would relate to a what percent? You asked a really good question here, Noel, because this one will get people stuck. Naturally, a 98% confidence interval relates to a what alpha level? Well, that's a 95%. 95 relates to 5% alpha. 98%, because it's complements, relates to a what percent alpha? %, relates to a what? Not good guess. Good guesses. 2%. They are, does that make sense that these values are complementary? So 98 and 2 add up to 100 because it's like inside outside. But here's the thing. Since we're on, this is if it's a does not equals test. If it's only a greater than test, how much would it be? Here's the hint. This is the two-tailed test on the screen right now, which would be for these both. But if we're just doing the greater than test, how much would it be? Does that make sense? If you're doing the does not equals test, it's both of these. But if you're just doing the greater than test, how much would it be? So that's 2%. But if you're just doing the greater than test, how much would it be? You see, it's symmetric. So think about how it's symmetric. Because we're only doing the confidence intervals naturally relate to a two-tailed does not equals test because two tails. Yes. You would have it. You'd cut it in half. So what would it be? You're right. You'd cut it in half. You'd cut the 2% in half. And that would leave you with only over here 0.01. That's huge. Yeah, 0.01. Because you're just doing half of what it was. So you're just taking that right there, just the half of it. Just one side, which if you think about that, it's just this over here. So you're just doing a part of it. You're only doing the greater than test. So the confidence level, the level of significance of the alpha is going to be 0.01. Since they're doing a one-tailed test, we have the areas right there. We have it. Exactly what you said. Hopefully visually to help. Check answer 100. Woo! It's a tough one. That's a good... No, you picked one of the toughest questions. Really good job. It's probably going to help a lot of people. Most of this is like the whole chapter. It's a lot. If you can do this question, you understand... It's a good question to know if you're ready for the test. I mean, like, if you can't do it, it's all right. But if you can do that question, like, this is a joke, this is easy. You understand a lot of concepts to do that one. It requires pretty much most of the chapter. It didn't do type 1, type 2 error, but most of it. This right here, 90% confidence interval. Very similar. We could do this one. Or if you have another one, Noel, let me know. That was a really good deep dive in that question. It was a good one. I'm gonna fall asleep. Got up at like 5:30 this morning. Yeah, I think so too. There's some questions I like, some questions I don't like. This one looks pretty good. This is a quick one. In a poll, the president's approval rating was 54% in a daily tracking of 1,100 randomly sampled adults. Make it 90% confidence intervals. Yeah, let's do which of the following. We'll do that next here. I'll do this one real quick, and then we'll do the one you want. So you know it. What we're going to do here is we're going to do notation. Just to show you, and I'll do this one quickly here. Once again, if you want a question done more slowly, swing by office hours and ask the question, and we'll do it, and we'll go into depth, and I'll take your questions while we do it. So this is p hat, because that's the proportion. Q hat is 0.46. This is equal to 0.54. This did not give us x. We could figure out x, but we don't need to. And then 90% constant is a z of 1.645, and we'd give that to you on a test. So p hat plus or minus z star, which has been obtained, p hat q hat over n square root, plug in the numbers of 0.54 plus or minus 1.645 square root 0.54 times 0.46 over 1,100, and then we start solving out. 0.54 times 0.46 divided by... We're just speeding through this to get to Noel's question. So 2.5%. Okay. Please have me enter in as percentages. 2.5%. So 0.515, 0.565. Based on the confidence interval, test the null that they have a 49% approval rating. I reject that because the confidence interval of the null hypothesis, because the rating of 49% is not in the interval. We got it. There we go. If you know the formulas, once again, if you know how to figure out your notation, you can usually solve these a little bit quickly. It matters, so knowing it all. Which of the following statements are true? And so yours has statements. Let me see, which of the following statements are true? Is it these, Noel? Here we go, it's this one. There's a lot of these. These are all theory. You can do much of theory. Yeah. Okay. It is better to use an alpha of 0.05 than an alpha of 0.01. Alpha is complete. I'm not even reading their answers. Alpha is completely decided by the researcher. Using a 0.05 alpha would increase your type 1 error because your alpha rate is your type 1 error rate. 1, 2, AB. Check out class. We go over these a lot. Or ask questions. Ask questions in the comments. Post a question in the if you're watching this right now, post a question in the comment. Ask me a question. I'll probably hop on YouTube and I'll try to answer it. So just drop a question, drop a like, like, subscribe, classic YouTube stuff. And so it just depends. If you use 0.05, it's more classic. So it's, here we go. I think is it. A lower alpha lowers probability type 1 but increases. Yeah, it's give and take. There's no right level of alpha. It's just pretty much everyone uses 0.05. There's no right level of alpha. If we use an alpha of 0.01, the p-value of 0.001 is statistically significant. How do we know if a p-value is statistically significant? A p-value is statistically significant when it is what to what. This is a huge thing you should know. Very important learning objective that this will answer this. A p-value is statistically significant when it is what to what. A p-value is statistically significant when it is what to what? Kind of. That is the assumed alpha unless otherwise stated. Statistical significance always means p-value less than alpha, but we usually assume alpha is 0.05. So you can change your alpha, but it is assumed to be 0.05 unless otherwise stated by the researcher or who is ever doing the research, I guess, the researcher. So this says that alpha is 0.01. So is this statistically significant? Noel. So you look at the alpha is 0.01, p-value is 0.001. So is that statistically significant? Yes or no? So remember, p-value less than alpha is statistically significant. So you got to write down your p-value, your alpha, and say, is my p-value less than alpha? So is this statistically significant? And what we could do, yeah, perfect answer. Great job, Noel. Because the p-value is 0.001 and the alpha level is 0.01. So we ask, is 0.001 less than 0.01? Because they stated that, and the answer is yes. P-value less than alpha. So that is true. No, you did totally fine. Great job. So that's true. And make sure I don't click the wrong button here. If we use a p-value, an alpha of 0.01, then we reject the null hypothesis if the p-value, that's the same thing. They're just wording it differently. You reject the null when the p-value is low, it's lower than alpha. So that is true also, unless I'm misreading these. You reject the null when the p-value is low, definitely true. If the p-value is 0.01, we reject the null for any alpha level greater than 0.01. They're really going crazy on this whole p-value alpha thing, but this is true. If you have any alpha level greater than p-value, which p-value then would be less than alpha, that is true. So a lot of truths. I mean, the main learning objective of that was when p-value is less than alpha, reject the null. Alpha can be decided by the researcher. Does that make sense, Noel, right there? Like, these three literally cover if p-value is less than alpha, reject the null. Reject the null means statistically significant, i.e. low p-value, lower than alpha. And you can use whatever alpha you want, but it's a type 1, type 2 error exchange. Like, you would be trading off type 1 versus type 2 error. Do a few more of these. Let's do quick questions right here. So what is the name of the threshold that determines when we reject the null? What is that bar that, so do you know that one, Noel? Just, this is what the researcher picks. Don't even look at their answers if you can. Like, the best thing you can do for these is to not look at their answers, but what is the name of the standard a researcher uses at which point if p-value is lower, they reject the null? The threshold, like if we get a p-value lower than this, I'm gonna reject the null, and the researcher can pick it, usually assumed to be 0.05. What is it called? What is it called? Good review question here from the last one. It is your alpha level. Yep. I call it alpha. It's your alpha. It's how significant you want results to be to say they are statistically significant. A p-value is smaller than the level of significant. What do? Don't read their answers. Don't read their answers. The p-value is smaller than alpha. Remember, we just saw alpha is level of significance from the last question. A p-value is lower than alpha. What do? Don't even read their answers. It would mean two things. We would do this, and it means it is this. So the p-value is low. If you're in my class, you should know the end of that sentence. We reject the null. Exactly. We reject the null. The p-value is low. We reject the null. We got statistical significance. Boom. When the p-value is high, just let it fly. Do not say that except word. That's a bad word right there. Don't say except. What is the probability that a test correctly rejects the false null? The probability a test correctly rejects the false null. We see a few things here that we've already covered, so maybe do process of elimination, because you should have sayings for some of these. But what is the probability? You see, you might choose something wrong, or don't worry if you get it right. I have a feeling what people might choose wrong. Well, type 2 error is when the null is false and we fail to reject it. That's what a type 2 is. Take another guess. Give me 30 points. Good guesses. Type 2 is a false negative when the null is false and we fail to reject it. So what's interesting is that is actually the opposite of this, or the complement of this. What you picked right there, and don't worry, is actually the complement of this. Type 2 error is known as beta. We're looking for 1 minus beta, which is the equation for statistical what? You might choose something else now because you're like, oh, statistical this? No. Don't worry if you get it wrong. I'll give the answer. Power. Power is the ability to correctly reject the false null. And we talked about this yesterday in class, how if you were to try a pepperoni of a pizza versus a whole pizza, it'd be easier to understand if the pizza is good or bad. Sample size impacts power, alpha level impacts power, and also effect size impacts power. So power is the ability to correctly reject the false null. I prefer to say power is the ability to find results when results exist. What is the name of the difference in the null versus the true parameter? What is the difference between the null and the truth? Once again, process of elimination will really help right here. You should have it down to 1 or 2 things. What is the true difference between the null and the hypothesized value? Don't worry about getting it wrong. Try process of elimination. What is the true difference? We talked about this a lot yesterday in class. I like doing all these multiple choices. This is where I talked about you can go to the hospital and have a cough, or you can go to the hospital on a stretcher. This is a difference in what? This is a difference in what? It's a concept from yesterday. Don't worry about being wrong. If we go process of elimination on this, we can go through each one and think of what we know they are. Alpha level is the significance. Oh, good Noel, good process of elimination. Do you want to bet on one of those? I'll throw you points. Take a guess on one of those. You've process eliminated it down to 2 choices, and the right choice is contained in there. So type 1 error we know is when the null is true and we reject it. That's what a type 1 error is. Doesn't sound anything like this. Alpha level is the significance that a researcher decides on by which point they'll reject the null. So it's the level of significance they do a test at, determined by the researcher. Doesn't sound like this. So you're between 2 of them. Which one would you bet on? Good guess. I'm going to throw you the 5,000 again. It's not critical value. I rarely to never mention critical values. Critical values are used a lot of times for the point at which you reject nulls calculated, but since we let software do it nowadays, I don't have to calculate critical values anymore. It's an old way of doing stats. You'll never really hear me talk about them, and they won't be on the test. So the answer is effect size. The effect of the treatment, we could say. Because we talked about yesterday with pizza, if your friend says they're the best pizza maker in the world, but they're really the second best, that's a small effect. It'd be hard to tell that they're only the second best. But if they're serving you horrible pizza, you'd be like, dude, this is so easy to detect because their null is that they're a great pizza maker, and the truth, because that's the true parameter right there, because the null, I'm a great pizza maker, the truth, I'm a horrible pizza maker, it'd be easy to detect that. So that's the difference between, it's the effect between what they claim and what the truth is. And that impacts the power of a test because when there's a bigger effect, it's easier to detect. Like imagine I were to play my brother in basketball, or I were to play LeBron James, who would be easier to tell that I'm better against? Wait, that I'm worse against? It'd be easier to tell that I'm worse against LeBron because LeBron is awesome. And then my brother and I would be closer in skill. He would still beat me though. So effect size is the difference between the hypothesized value and the true value. Which of the following statements is correct interpretation of a p-value that is not very small? That means the p-value was higher than the level of alpha. We'd fail to reject the null. And what we saw was not surprising because it was a likely result. High p-value, high probability. So what we saw was not surprising. We would fail to reject the null. By not surprising, we mean high probability because p-values are probabilities. Fail to reject the null. When the p-value is high, just let it fly. Kind of, when you look at the distance between the values. Does that make sense, Noel? Let me know. We do a full lecture on it. We did a full lecture on it yesterday. So we just did that whole section right there of multiple choice. I don't think there's any other multiple choices. It's hard to do these full assignments. A lot of really good questions in here. Which of the stellar statements can be made? The null is true and we reject it. That's a type 1. The null is false and we fail to reject it. Once again, the null is true and we reject it. Type 1. The null is false and we fail to reject it. Type 2. 1 and 3. 1 and 2. Spam filters. I might have just enough time. Let me see. Might be a multiple choice. Let me see. I'm gonna try to do that, Noah. That's an easy one. What type of error is made when a true null is rejected? Type 1. We just did that. What type of error is made when the null is false and we do not reject it? That's failed to reject. Type 2. These are the same question, but they're interesting. Man, we've almost done a lot of this. This is the same thing we did earlier, just proportion intervals. Here we go. Okay. We'll end with this one right here. And spam filters. We just did a lot of the questions. And take time, review them, write down the terms, try to make up your own examples. Okay, spam filters. So I'm pretty certain they need evidence that it's spam. Does that make sense, Noel? Like your spam filter lets emails pass through, and then they're looking for evidence that it may be spam. It literally says it right here. So when we see evidence it's spam, oh no, you're fine, let's do it. I got time. I teach at 11:20, so I'm good. I got 15 minutes to finish up and get to class. You're good. So evidence means, I got up too early. Evidence means we're looking for the what, the null or the alternative. Evidence is related to the what. Evidence is related to the what. This is a huge learning objective. Evidence is related to the what, the null or the alternative. Evidence is related to the what. Goes back to the courtroom trial examples. So write these down if you're practicing. Evidence is always required to believe the, where you get it wrong, the alternative. The alternative is the evidence-based claim, and the null is believed by default. Like in a courtroom, you're innocent until there's evidence of your guilt, so they'd reject the null. We don't try to have evidence to retain the null, not reject it. We have evidence to reject the null for the alternative. So the evidence is for the alternative. We find out evidence that it is a bad email. We don't need evidence that it's a good email. We need evidence to reject the null, that it's a spam email. So what we would do right here is we'd write the following, and we would write the null is good email, and the alternative is spam email. Does that make sense, Noel? We're looking for evidence for the alternative that it is a spam email. So with this alternative right here, what is a type 1 error? This is how to do it, and do it on the test. In a type 1 error, the null is true. So what is a fact in a type 1 error? In a type 1 error, that's your 1, the null is true. In a type 1 error, the null is true. So what's a fact of the world in the type 1 error? It's a fact. Tell me a fact. In a type 1 error, the null is true. In a type 1 error, the null is true. So what's a fact? This is a fact. What's that mean? What's that fact mean? Tell me, what does it mean the null is true? What's that mean? If the null is true and it's a fact, what does that mean? The null is it's a good email and that's true? What's that mean? How much sugar I get? Not horrible. Yeah, it's a fact that it was a good email, but in a type 1 error, we what the null. So in type 1 error, it's a fact that it's a good email that we should read, but we whatted it. In a type 1 error, the null is true. We rejected it, so we would believe what? So it is a good email, but we're going to believe what with this email? In a type 1 error, it is a good email, but we're going to believe what? In a type 1 error, it is a good email, but we're going to believe what? In a type 1 error, we're going to believe it's spam. It's actually type 1 error, the null is true. It's a good email. And we reject that and we believe it is spam because we make an error. It's when your spam filter is a little too crazy. In a type 2 error, so we'll put a 2 right here, the null is false. That's what you see me doing when I do these little things right here. In a type 2 error, the null is false, but we failed to reject it. So it's false that it's a good email, but we're not going to reject that. It's actually spam, so you can put the true down here. This is a true down here. We don't talk about the alternative being true in this. I mean, it would add a lot more wording to it. But if it's false that it's a good email, logically it'd be true that it's a spam email, because in a type 2 error, the null is false, but we failed to reject it. So we'd believe it's still a good email, but it's actually spam. Does that make sense? In a type 2 error, the null is false, so it's not a good email, but we failed to reject it, so we still believe it's a good email. So it'd be getting an email that is spam, but believing it's good. When the filter allows spam to slip through, would be a type 2 error, because the null is false and we failed to reject it. What type of error is it when a real message is classified as junk? It's type 1 error because the null is true and we rejected it. Some filters allow a cutoff. Suppose it has a default cutoff of 50 points, but you move it up. So that means you're allowing more things through. I might just answer this one myself. If you're allowing more things through, you're going to get more junk. So you're going to have more false negatives. I should graph it out again. It's probably helped me do it. Wait, it requires less evidence. We know this. Okay, wait. It's gonna require more evidence. Okay, wait. Because the points. Okay, so they're saying it has to have 50 points. You push it to 60 points. So you require more evidence. So it'd be a lower alpha. Lower alpha is more evidence. That makes it easy. More evidence means you're asking for a lower alpha. Don't even worry about how the points work, but higher points means you need more evidence. That's what they're saying. So if you require more evidence, that's analogous to having a lower alpha, because you're saying I'm making it harder to reject. I need more evidence to reject the null. What impact does changing the cutoff have? If you lower your alpha, alpha is literally type 1. So you would decrease your type 1, but increase your type 2. They're inversely related, and that's a huge thing right here. So you would decrease your type 1 by lowering alpha and increase your type 2. And we got it. I did those last ones a little bit quickly, but with that, because I have 10 minutes to get to class and set up everything and get going. Noel, great job. Check out the other videos where I go more in depth and probably draw it out. Bye for now, everyone. Bye.